During hovering flight, a helicopter maintains a constant position over a selected point, usually a few feet above the ground. For a helicopter to hover, the lift and thrust produced by the rotor system acts straight up and must equal the weight and drag, which acts straight down. While hovering, the amount of main rotor thrust can be changed to maintain the desired hovering altitude. This is done by changing the angle of incidence of the rotor blades and hence the AOA of the main rotor blades. Changing the AOA changes the drag on the rotor blades, and the power delivered by the engine must change as well to keep the rotor speed constant. The weight that must be supported is the total weight of the helicopter and its occupants. If the amount of lift is greater than the actual weight, the helicopter accelerates upwards until the lift force equals the weight gain altitude. If thrust is less than weight, the helicopter accelerates downward. When operating near the ground, the effect of the closeness to the ground changes this response. The drag of a hovering helicopter is mainly induced drag incurred while the blades are producing lift. There is, however, some profile drag on the blades as they rotate through the air. An important consequence of producing thrust is torque. Newton's third law states that for every action there is an equal and opposite reaction. Therefore, as the engine turns the main rotor system in a counterclockwise direction, the helicopter fuselage tends to turn clockwise. The amount of torque is directly related to the amount of engine power being used to turn the main rotor system. Remember, as power changes, torque changes. To counteract this torque-induced turning tendency, an anti-torque rotor or tail rotor is incorporated into most helicopter designs. A pilot can vary the amount of thrust produced by the tail rotor in relation to the amount of torque produced by the engine. As the engine supplies more power to the main rotor, the tail rotor must produce more thrust to overcome the increased torque effect. This is done through the use of anti-torque pedals. During hovering flight, a single main rotor helicopter tends to drift or move in the direction of tail rotor thrust. This drifting tendency is called translating tendency. To counteract this drift, one or more of the following features may be used. All examples are for a counterclockwise rotating main rotor system. The main transmission is mounted at a slight angle to the left, when viewed from behind, so that the rotor mast has a built-in tilt to oppose the tail rotor thrust. Flight controls can be rigged so that the rotor disc is tilted to the right slightly when the cyclic is centered. Whichever method is used, the tip path plane is tilted slightly to the left in the hover. If the transmission is mounted so that the rotor shaft is vertical with respect to the fuselage, the helicopter hangs left skid low in the hover. The opposite is true for rotor systems turning clockwise when viewed from above. In forward flight, the tail rotor continues to push to the right, and the helicopter makes a small angle with the wind and the rotors are level and the slip ball is in the middle. This is called inherent sideslip. When hovering near the ground, a phenomenon known as ground effect takes place. This effect usually occurs at heights between the surface and approximately 1 rotor diameter above the surface. The friction of the ground causes the downwash from the rotor to move outwards from the helicopter. This changes the relative direction of the downwash from a purely vertical motion to a combination of vertical and horizontal motion. As the induced airflow through the rotor disc is reduced by the surface friction, the lift vector increases. This allows a lower rotor blade angle for the same amount of lift, which reduces induced drag. Ground effect also restricts the generation of blade tip vortices due to the downward and outward airflow making a larger portion of the blade produce lift. When the helicopter gains altitude vertically, with no forward airspeed, induced airflow is no longer restricted, and the blade tip vortices increase with the decrease in outward airflow. As a result, drag increases, which means a higher pitch angle, and more power is needed to move the air down through the rotor. Ground effect is at its maximum in a no-wind condition over a firm, smooth surface. Tall grass, rough terrain, and water surfaces alter the airflow pattern, causing an increase in rotor tip vortices. The Coriolis effect is also referred to as the law of conservation of angular momentum. It states that the value of angular momentum of a rotating body does not change unless an external force is applied. In other words, a rotating body continues to rotate with the same rotational velocity until some external force is applied to change the speed of rotation. Angular momentum is moment of inertia, mass times distance from the center of rotation squared, multiplied by speed of rotation. Changes in angular velocity, known as angular acceleration and deceleration, take place as the mass of a rotating body is moved closer to or further away from the axis of rotation. The speed of the rotating mass increases or decreases in proportion to the square of the radius. An excellent example of this principle is a spinning ice skater. When skaters extend their arms, their rotation slows down because the center of mass moves farther from the axis of rotation. When their arms are retracted, the rotation speeds up because the center of mass moves closer to the axis of rotation. The reason for this is that the distance between the center of mass and the axis of rotation, times the rotational velocity of the mass, will try to remain constant. The rotor blade rotating about the rotor hub possesses angular momentum. As the rotor begins to cone due to G-loading maneuvers, the diameter of the rotor disc shrinks. Due to conservation of angular momentum, the blades increase speed even though the blade tips have a shorter distance to travel due to reduced disc diameter. The action results in an increase in rotor RPM which causes a slight increase in lift. Most pilots arrest this increase of RPM with an increase in collective pitch. This increase in blade RPM lift is somewhat negated by the slightly smaller disc area as the blades cone upward. When a rotor blade of an articulated rotor system flaps upward, the center of mass of that blade moves closer to the axis of rotation and blade acceleration takes place in order to conserve angular momentum. Conversely, when that blade flaps downward, its center of mass moves further from the axis of rotation and blade deceleration takes place. Keep in mind that due to coning, a rotor blade will not flap below a plane passing through the rotor hub and perpendicular to the axis of rotation. Either dampers or the blade structure itself absorbs the acceleration and deceleration actions of the rotor blades, depending upon the design of the rotor system. Thanks for watching.